Hello, I'm Dr. Thomas Howarth, a researcher and lecturer at Queen Mary University of London, and also the deputy of the MSc Astrophysics programme. In this short talk, I'm just going to give an overview of the kind of modules that we teach, and the research projects that we offer, and how they all tie together in the course, and also some of the value of the course. So starting off just for a few moments, I want to tell you a little bit about myself. So as I mentioned, I'm a researcher, and my main problem that I'm interested in is how planets form and how that is affected by the star formation process. So here we've got a lovely image from the James Webb Space Telescope of the Tarantula Nebula. It's a huge star-forming cloud forming a great many stars. And planet formation happens around young stars which are in these kind of environments. And actually they form from what we call circumstellar disks. I'll mention these again a little bit later in the talk. And in these harsh star-forming environments, there's lots of radiation from other stars that form in these big clustered groups. And that radiation can shine on the disk. So here we have a disk, and here's a massive star that's shining light on it and stripping material from the disk. And that can make the disk a bit less massive, it can make it live for less time. And my personal interest in my research is understanding how that affects the planets that we end up with. And I try and address that with computer simulations. So here are some models of a disk, which is the red bit here, being shone upon from this direction, and it loses material. And I don't just do theory work, I do predictions of what real observations should look like, so with a telescope, and then you can compare those with the real thing and test the theories. So in my research I use a lot of computer simulations, but also real observations too, with state-of-the-art facilities. So that's a little bit about myself. Now onto the Astrophysics MSc. So we have 10 elective modules that you can choose from. You actually choose 7 of these across a 1-year or 2-year part-time MSc Astrophysics. And the 8th, so you do 2 per term, per semester. And so the 8th module is this compulsory research methods training. So you choose 7 in topics of astrophysics and this compulsory research methods. And those taught modules are worth 2/3 of the degree, and the remaining third is made up by this compulsory research project, which I'll get to at the end. And this is a really important part of the degree and one of the most valuable bits as well. So I've got these icons here sort of summarizing some of the different areas that we look at. So in cosmology, galaxies, general relativity, astrochemistry and radiation transport, planets and their formation, stars and how they evolve, our solar system and astrophysical plasmas. And what I'm going to do now is just take a real quick whirlwind tour of these modules just to show you the kind of material that's in them. So it's going to be fast, so don't worry if it doesn't all make sense. The point of the degree is you can spend 1 or 2 years learning this. So the radiative transfer and astrochemistry module is the one I teach, and so you're going to get a bit more information about it. So the underlying point of radiative transfer is to understand how light is emitted, how it moves through space, and really what this comes down to from an astronomer's perspective is this is how we actually work out the details of what's going on. A pretty picture's nice, but it's radiative transfer that tells us how hot that cloud is, how stuff is moving, what it's made of, and that what it's made of also translates into this astrochemistry angle, which we look at in the course. So what are actually things made up of? How does that change over time? And then there's this thing at the bottom called radiation hydrodynamics. So with the upper stuff we can understand this cloud and what it's made of and what it's doing. But the dynamics is how the light actually makes things move. So in this example, we've got a planet orbiting a star so close that the star's light is stripping material off the atmosphere. And every time the planet gets between our eyes and the star, it makes it look a lot fainter. So this line is how bright the star looks, and when the planet comes around, you'll see that it gets a lot fainter. So here is radiation affecting a planet's atmosphere, making it lose material. Another example is this one, where you can see 2 star-forming clouds. They're going to collapse and start making little stars that you'll see. The difference is that the one on the right accounts for the fact that the really big stars emit a lot of energetic radiation, and that heats the gas up and makes it expand. So we would be looking at not just how we learn stuff from light, not just how we can figure out what stuff's made of, but also how light affects the way things move. And as I said, I'm not going to go into this much detail about the other modules. It's just purely because this is the one that I teach. I just wanted to highlight that in addition to lectures and problems classes and things, and so you get things like notes and slides. I also develop applets for my students to look at as well, to explore in a bit more detail, or maybe in a more intuitive way, what some of the equations are doing. So here we have the equation describing how the intensity of light gets fainter as it shines through a medium. So if you shine a torch through a foggy day, then it gets less bright, the light, as you go through the cloud, through the fog. And how that happens depends on how dense the cloud is, how far you're going through the cloud, and this thing called the opacity. And so here, if we had the live app, you could drag these sliders and see how the brightness of this star changes behind this cloud. So as I make the cloud less dense, say, or less thick in this case, so if it's quite a thin cloud, the star looks brighter. If I make it thicker, it looks fainter. Here we're changing the wavelength of our light. So at shorter wavelengths, the light gets blocked out more than at long wavelengths. And here you've got changing the density of the cloud as well. So there are, from many examples, these sorts of apps developed which allow you to explore the concepts in a slightly different way, a more visual way. So everything is going to go a lot quicker now. Moving on to cosmology. So we have two cosmology modules. There's physical cosmology and advanced cosmology. So in physical cosmology, we're looking at things like the structure of the universe, the Big Bang, inflation, expansion, the ultimate fate of the universe. And in advanced cosmology, what we add in is the introduction of structure into the universe. So this is a simulation of structure forming out of the universe. We won't be quite doing this in advanced cosmology, but using perturbation theory to analytically model the introduction of structure into the universe. So this here is a movie of filaments of dark matter with galaxies forming, clusters of galaxies forming within them. Relativity and gravitation is very analytic, very pen and paper maths heavy. And so this is looking at Einstein's field equations, how light propagates in a curved space-time, things like the Schwarzschild and Kerr metrics, and the mathematical description of black holes. It's very interesting, but a bit more mathematically challenging. The physics of galaxies and the galaxy. So the physics of galaxies is actually a third-year course that you can choose. However, typically we recommend just going to the galaxy, which covers basically the same material but with extra stuff and is more tailored for a master's level course. So these modules both look at galaxies and their properties, so things like their morphologies, what makes up a galaxy. The dynamics of stars in clusters. So in this movie you can see the stars moving around, interacting due to their gravitation, and so you'll be understanding how stars move in different kinds of potentials. There's radiative processes in galaxies, which I've kind of already covered briefly in the talk about my module. So this is things like H2 regions, so this is massive stars ionizing their surroundings and blowing bubbles in the gas. So how does that affect the galaxy and the way it evolves? And also things like galaxy dynamics, so and evidence for dark matter. So as you go out in a galaxy, we'd expect the rotation to follow the dashed line, but actually it follows this solid line. So what's causing that? Well, one of the suggested solutions is dark matter. Astrophysical plasmas. So a plasma is basically an ionized gas. You've got all of your electrons stripped off of your atoms, or at least from hydrogen. And so in this module, we will be looking at how particles move in these plasmas, which obviously is linked very strongly to the structure of the sun and the solar atmosphere. We just saw a nice solar flare there. This module also covers magnetohydrodynamics, where you introduce magnetic fields that affect how these charged particles move. And of course, the solar wind is linked into this topic, which is linked to space weather, which is becoming increasingly important given the impact we think it can have on satellites. It's worth noting briefly that the group here at Queen Mary is very involved in missions like the Parker Solar Probe, which has flown through the solar atmosphere, and I'll come back to that when we talk about research projects in a little bit. Or in fact, here is a nice movie from the Parker Solar Probe. So this is real, this isn't a simulation or anything, flying through the solar atmosphere. So one of the projects we'll mention briefly later is looking at data from this instrument. Extrasolar planets and astrophysical disks. So this is looking at the properties of planets. In the last decade, the number of planets we've discovered has exploded to more than 5,000. So this plot just shows how massive the planets are and how far they are from the star. Essentially, it's written down as orbital period, but that's kind of the same thing. And you can see what we've got here: the Earth. This is Jupiter. There's Mercury, and so there's a really wide range of properties of planets that we've discovered now, and we want to understand that. But it's also interesting to see their different characteristics, things that we don't have in our solar system, like hot Jupiters and super Earths. So we'll look at the properties of planets, how we detect them in the first place. So for example, with the transit method, where the planet passes in front of the star and makes it look fainter periodically. So in addition to this, you'd look at all kinds of other detection methods that we have. And then the astrophysical disk side of things is looking, well, from my perspective, mostly at planet-forming disks. So here you've got a young star with a disk around it, like this. And then this is the same sort of thing here, but rotated 90 degrees, so you can't really see the star. And these are where the planets form. And these are what get evaporated, and what I'm interested in. But astrophysical disks could equally apply to things like accretion disks around black holes, for example. And in addition, into this module, there's the theory of planet formation. So how do you actually get planets from these disks? So this is a real image, by the way. Here's your disk, and here is a planet that we've directly observed forming in the disk. The solar system, we're almost there now in our whirlwind tour. We'll obviously look at things like the terrestrial and the giant planets of the solar system. Orbital mechanics of 2 and 3 body problems. So 2 body problem is an object and something else orbiting around it. 3 body is, well, when there's 3 bodies. So this is an animation showing the orbit of the James Webb Space Telescope around the L2 point and the Earth and the Sun. So that will make a lot more sense following this module. Tides are another thing that's looked at. So obviously we have the tides on the Earth. This is Enceladus, which is a moon of Saturn, which is being tidally perturbed by Saturn and is causing these great big plumes of material to be launched out of water, possibly. So tides play an important role throughout the solar system, and also things like resonances. So I'm not going to explain what those are, but in a second these inner planets will disappear, and you see that every time these inner 2 planets line up, they point at the outer one. Okay, they always line up in a line when they cross trajectories. And this is a resonance. To find out more about what that is, you'll have to take the course. And additionally, this course also looks at things like asteroids, comets, and impacts. I think the final module is stellar structure and evolution. So of course here you're looking at the structure of stars, how they produce energy, how it moves throughout the interior of the star and eventually escapes. How stars form from clouds of gas and dust in the galaxy. And the stellar evolution. So they're born, they evolve, they burn fuel in different ways, and eventually they die and leave something like a planetary nebula or a neutron star or a black hole. So this is stars, how they work, how they're made in the first place, and how they evolve and eventually die. So that's the whirlwind tour of the modules, but how are they actually taught? Well, typically because we have people come in from potentially quite large distances for the master's course, we condense the teaching into as few instances as possible. So rather than having 1-hour sessions, we have a single 3-hour session per course per week. So if you're doing 2 modules in the semester, that's 2 3-hour slots. And these are not 3 hours of sitting there listening to the lecturer talking at you. They are typically 1 or 2 stints of material with breaks, and then problem solving, which is done interactively. So usually problems are set before the session, and the idea is we sort of go through them and understand them together in the final hour or in the final whatever time is of that 3-hour slot. And that interactive problem solving is really important because the exam is going to be a problem solving exam. Exams do not necessarily involve regurgitation post-COVID because often they're still online, so there is no point asking you to remember stuff. And actually, it's much more valuable to be able to solve problems with the material in front of you. That's how things work in reality when we're trying to solve real problems. So these interactive sessions, yes, you will be learning material, but the idea is also to teach you how to solve problems, and that will be supported with coursework, though not that much. and this will all build you up to being able to tackle a problem-solving exam. Research projects. I mentioned this is really important. So it's not just a third of the degree. We'll come on to this again in a second, but if you're interested in an academic career, then what will really be looked at is your research project and how you do there. So there are three main approaches to tackling problems in astronomy and cosmology. There is analytic pen and paper theory, there is running computer simulations, and there are observations. And we offer projects in all three of these areas, and I'm going to just summarize some of them now, again with a bias to the kind of stuff that I work on. So this isn't exhaustive. So an observational project that I'm preparing for this year is combining James Webb Space Telescope and Hubble Space Telescope data. So this is the Southern Ring Nebula you can see here on the right, which was imaged with Hubble about 15 years ago and was imaged very recently with the James Webb Space Telescope. So what you could see a minute ago was the Hubble image, and I'm here dragging the JWST image across the top. So the JWST image is great, fantastic. But what can we do with it? Well, this is a nebula around a dying star, and the material is expanding away from the star. And because there was 15 years between the Hubble and the JWST data, we can actually look for things moving in that time. So I've had a little look at the data. This is just one example. It's not the best contour that I've got here. This is brand new stuff from the last few weeks. So this is orange blob is a clump of material in the Hubble Space Telescope data, and then this contour here is the same clump of material in the JWST data. So it has moved. So we can turn that into a velocity. We know the time between the observations, the distance travelled, and we can work out how fast these things are going. Now I've done a pretty rough and ready job, and I think these things are going faster than we expected. So obviously that needs to be checked and verified, and there's a whole bunch of these different clumps that we can look at and check if that's consistent. But really the question is, why are they going faster? Is something accelerating these little blobs of material in the cloud? Could well be something called the photoevaporative rocket effect, where light shines on the back end of a clump, drives material away and launches it in the other direction like a rocket. So who knows? It's an unsolved problem. It's at the cutting edge of what we know. This is brand new data from James Webb Space Telescope, and this will be a master's project. Now moving on to some other things that people have done. So in terms of pen and paper theory, I don't know very much about this as a project, unfortunately. But I can just give the general idea, looking at things like gravitational lensing by black holes, so describing the warping of light of some background source by a black hole in the foreground. Now in this case the gravitational lensing is by a galaxy, so this is some background object that's been lensed by this heavy thing, this massive thing here. But this project was using theory to look at the role of black holes in this, and just a token direct image of a black hole that we have here. So we've looked at an observational project, a sort of pen and paper theory one. Here's another numerical simulations one that I've offered, doing M-body simulations. So this is the solar system, and here is a star that's going to fly past it and cause some havoc. So it's coming in close enough to eject two of the planets. Bye-bye these ones, I forget which ones they are. And it's actually captured two others. So this is interesting because it's produced some what we call rogue planets that don't orbit a star, and has obviously completely affected this planetary system and made a new one. So these flybys are expected to happen, though with a frequency that's currently debated. So in this project we could be looking at things like how close does the flyby have to be to actually affect the planets? Does it depend on the angle that the star comes into the planetary system at? Things like that. To exploring the disruption of planetary systems by other stars, or black holes, for example, we could do. This project's using machine learning. So really sort of data intensive stuff that's really valuable in the workplace. So definitely not going to go into the details and probably couldn't tell you them all. But what they've essentially done is developed neural networks that work in a way that's analogous to the brain, and trained it to try and solve physics problems, with the ultimate goal being to solve a problem in astrophysics. But here is just, this is something I marked this year, assessed this year. And so this is a damped harmonic oscillator, and this is what they were they were testing different neural network approaches on trying to predict from some limited amount of training how things should behave. So basically trying to predict the laws of nature based on limited sort of information. And some of these types of neural network do a lot better than others. I already mentioned the Parker Solar Probe, but this was a title from last year, I believe, so exploring the sun's atmosphere with the Parker Solar Probe. So I don't know exactly what this entailed, but again, it's a sort of instrumentation, observational project, taking data from this spacecraft that's flown through the solar atmosphere. And I know the group at Queen Mary doing work on plasma physics does things like numerical simulations of the plasmas, trying to understand how they behave, and trying to explain and understand the observations that we're seeing from instruments like the Parker Solar Probe. Nearly done. I think this might be the last example. So this student built a hydrodynamics code from scratch of their own initiative. So obviously projects are offered, but if you choose to do something that interests you, then that is also fine. So here they have what's called a shearing box. So it's a box and they're dragging stuff across the top and it causes a vortex. And this is a simulation that they ran themselves and developed the code to do themselves from first principles. So this is pretty impressive. And I've probably given the impression that I understand the projects I offered, and maybe not some of the others so much. So like the cosmology ones, for example. But I just created a word cloud of the titles of projects that I've been given from the last couple of years. So you can see it's covering a really broad set of topics, including things I probably skimmed over a bit. So we've got observational stuff, equations. I didn't really go into any of the mathematical stuff particularly. Exoplanets, cosmology, the universe as a whole. This universe here is definitely linking to cosmology projects. There is numerical modelling, people looking at Venus. There's definitely projects on the solar system dynamics that I've not really highlighted so much. But there's a really wide range of topics that are worked on, and as I said, they should typically be sort of at the forefront of our knowledge. So that's the summary of the degree, but I just wanted to ask the question, what's the point? Why should we be thinking about doing a master's in astrophysics? Well, I think one of the things that's driven me is that it's fun. I enjoy learning about space and getting to work on understanding the universe better. I find it interesting. I find it rewarding and satisfying, especially when you get to start working on new data, like we're going to have in abundance from JWST. And in addition, though, to just being interesting, it does develop you, both from a sort of, personally at least, I find from a philosophical standpoint, seeing where you fit in the universe, but also, of course, it gives you the technical and problem-solving skills which are really important for these latter 2 points. So if you're interested in an academic career in research in astrophysics, the master's really gives you the skills you need to go on to be competitive for a PhD. And in particular, as I already said, the choice and your research project is really a strong asset for being considered as a candidate for a PhD program. PhD interviews often start with asking you to summarise your research experience to date, so this gives you that. But if that's not for you, then the skills you develop, they are viewed favourably in the industry as well. You're going to be you'll becoming technical problem solvers, usually with programming skills as well. I mentioned there was a machine learning or hydrodynamics code that were written. These are the ability to do these sort of things are sought after in the workplace. And just to emphasize that even more, people sort of say with astrophysics it's head in the sky, not so useful stuff. But here are just some examples from people often linked to me, so not even considering what's done worldwide, and also related to the single course that I teach. So this is just a very narrow subset of examples of where the stuff we work on has an impact. So my course is radiative transfer and astrochemistry, so to do with radiation. In the last couple of years, people I know have done things like develop ultraviolet light tools that would kill COVID-19 but not damage human skin cells. So it could be used, or it's not so relevant now that we feel we're over COVID, but could have been used at the time to treat rooms without hurting people. It's used by the UK Met Office to understand the climate and of the planet. It's used in sensors, understanding things like satellite sensors through something called canopy radiative transfer, so understanding how forest canopies reflect light. And this is my PhD supervisor's work and his team, turning an astrophysics code to study breast cancer. Just another example, so at one point in my career I was possibly moving into industry, thinking of working with this company Emacs, which looked amazing to be honest, and they developed software that models the propagation of light in optical instruments. So here there is they're involved in the design of the JWST telescope. So again, another possible application of the kind of stuff we learn in the radiative transfer course in industry. And finally, of course, the video game industry. You'll have heard the term ray tracing a lot. Can be used to make computer games look a lot more impressive. In my course, we actually build a ray tracing code in the second lecture. But no programming experience is required. Before we finish, just to mention, there is the PG Cert as well. So for the MSc Astrophysics, you can do it full-time and take a year about it, or part-time and take 2 years. The PG Cert is a 9-month part-time study worth, or equivalent to half a taught component. So this is 4 modules without a research project, but you can use this to transfer onto the MSc should you wish. So that's it. I hope this was interesting and not too much information. But to summarise, if you do an MSc Astrophysics at Queen Mary, you get to study the main areas of modern astrophysics research and the fundamentals that are really needed to address outstanding problems. You'll undertake a research project with an active researcher in the astronomy unit on a topic at the forefront of our understanding, so possibly with new JWST data, or looking into new equations or new numerical models. And these sort of skills are really valuable if you want a career in academia, but also in technical industry too. So thank you. And any questions, if this is an online event, then I'll answer them now. Otherwise, look me up online at Queen Mary and you can email me any questions that you have. Thanks.